So let's talk a little bit about implicit differentiation. It's basically a use of the chain rule, and I'll show you how in a second. So suppose you have this function here, and you want to find out what the slope of the tangent line is. I don't know, at 1. So you want to find out where the slopes are 0 on this. So it looks like you got there and there. Or perhaps you want to find out what the slope is at -2. Now, in order to do this, you would normally have to solve for y and get y as terms of the function x, do y prime, and then find y prime. You got y prime, set that equal to 0. That'll tell you where the slopes are 0. Or then take y prime, plug in -2, and that'll tell you what the slope is there at -2. The problem with this function, though, is y is kind of hard to solve for. You would have to use the quadratic formula with x, and it just gets really nasty. I would encourage you to try this, where you get it's y squared minus xy minus 3 plus x cubed equals 0. And you would use the quadratic formula here, where you would say y equals -b, where this negative x here is -b, and then it's just a mess. And so this is c, this is your b, and then a is 1. And it's a very difficult problem. So implicit differentiation basically says the following. It says, I still want to find dy dx, but I don't want to, I may not be able to solve for y in terms of x. And so how do you find dy dx anyway? And so the reason why it's called implicit differentiation is because we're assuming that y is implicitly a function of x, but we just can't, we either can't find it or it's very difficult to find. For example, if you had something like like tangent of xy equals e to the y plus I don't know, y squared, it would be impossible to solve for y. So how do you do it? Well, we're going to use the chain rule here to help us out. And so I'm going to take a little bit of time here and see if you understand the chain rule fully. So the chain rule says this. It says basically, suppose I have a z as a function of y, and then y is a function of x. So y is a function of x. And so the question might be, what is the derivative of z with respect to x? So z isn't a function of x, z is a function of y. Y is a function of x. So you go dz dy, and then dy dx, and you'll get your answer. So for example, and we're gonna do that in this problem up here. You could have z equals y squared, and then you could have y is, you don't know what it is, so y is just a function of x. So dz dx would be, so dz dx is the same thing as saying the derivative of, with respect to x, of y squared, because z is y squared, right? Z is y squared, because this dz dx can be written as d dx of z, right? So I'm just pulling it off to the side and then rewriting it like that, because z is y squared. Alrighty, so what this is equal to is, I'll pull this over here, it's dz dy, which is 2y, and then dy dx. This piece here, we don't know what it is, so we're just going to write dy dx. Done. So this is your answer. All right. So let's try another one. Let's suppose then that z is sine of y, and y is some function of x. We don't know what it is, or it's difficult to get. So then dz dx is, all right, so it's the derivative with respect to x of z, and in this case, z is sine of y. Yeah, that's right, that's right. Okay, so now we are going to just use the chain rule. So dz dx is dz dy, and then dy dx. That's how it works. It kind of looks like, and I said this in a previous video, it kind of looks like the dy's are canceling, and then you get dz dx. That's not what's happening. These just are equivalent. All right, so walking through this, we have dz dy is going to be, the derivative is going to be dz dy, and then dy dx. dz dy is cosine of y. And then we multiply times dy dx. And we're done. That's it. That's all we know. All right, so let me try another one, because it takes a little while to get used to this. Suppose z is natural log of y, and y is some function of x. So I'll put in the function of x here this time. Suppose y is x. Let's say sine of x. Sine of x. Okay, so if I want to find dz dx, I have to go through y first. So that's dz dy, and then dy dx. All right, dz dy is natural log of y. The derivative is 1 over y. And then dy dx is cosine of x. And we're done. This is cosine of x, and then y is sine of x over sine of x. And then we get cotangent of x. All right, so we're done with that, right? Now, what you could have done instead is suppose that the sine of x we didn't know. So suppose we didn't know what this was, and we just knew it was some function of x. So then we wouldn't know this piece, and what it would become is just 1 over y times dy dx. That's all we know. And so that's your answer. That's your answer if you don't know what y is in terms of x. So when we do this problem up here that I picked out, it's kind of similar to a homework problem. When we do this one here, we are going to use this concept. So here we go. Let me rewrite it and start over. Okay, so here we are. So here's the process. So you're going to take the derivative with respect to x of both sides. It's the first thing you do. All right, so I'm going to apply it to each term inside. All right, so the derivative with respect to x of x cubed minus the derivative with respect to x of xy plus the derivative with respect to x of y squared equals derivative with respect to x of 3. Now, some of these are real easy. The derivative with respect to x of x cubed is just 3x squared. We know that. The derivative with respect to x of 3 is 0, because 3 is a constant. The derivative with respect to x of y squared, now, this is the chain rule. This will be 2y times dy dx. Where did I get that? Well, if you just look back up here, y squared, right in here, we said z was y squared, and we had to find the derivative with respect to x of y squared. So we said, basically what we did was we set z equal to y squared to figure this out using the. All right, so if you just go back here where we were, every time you see, basically it's like this. Anytime you see a function that is in terms of y, and you're trying to find the derivative of it, you take the derivative with respect to y, and then you just write down dy dx. So this is the dz dy, and this is the dy dx. This is the chain rule. dz dx is dz dy times dy dx. All right, so let's not make this too complicated. Now what we have is the last part of this, which is this piece right here. Essentially, you want to do this. All right, so we have two functions, f and g. So we'll take f prime g plus f g prime. So when we do this problem, the derivative of x with respect to x is just 1 times g, which is y, plus f, and then derivative of y with respect to x is just dy dx. It's 1 times dy dx. And then this plus comes down. This plus is right there. All right, so what do we have left over here? We have 3x squared minus y minus x dy dx plus 2y dy dx equals 0. So before we go on, let's just see what we did. We took the derivative with respect to x on both sides of this right here. Anywhere there was just an x, we just took the derivative. Anywhere there was a constant, that's 0, right? If it's just y squared, if it's just y, you take the derivative with respect to y, multiply times dy dx. And then this piece here we had to treat carefully because that was the product rule. And the product rule says derivative of function times another function is this little formula right here. All right, so now when we're down to this step at the very bottom, what we do is we just get the dy dx's by themselves and move everything else over to the other side. So when we do that, we get negative x dy dx plus 2y dy dx equals y minus 3x squared. I changed the sign of these and moved them and added them to the other side. So now we can take out the dy dx, and we get negative x plus 2y equals y minus 3x squared. And now we want to solve for dy dx, so we're going to divide both sides by negative x plus 2y. We get dy dx equals y minus 3x squared. And then I'm going to, well, it's negative x plus 2y. It might be easier to write it as y minus 3x squared over 2y minus x. And there you have it. That's dy dx. So let's go back up and see what's going on with the graph. All right, so here we are. So me may have a question. What's dy dx at 1 comma negative 1? So what is this? So at 1, negative 1, over 1, down negative 1. We use a different color, red. And then what is dy dx at, let's say, 1 comma 2? So at 1 and then 2. All right, so what is that? So let's see, so we have our dy dx up here. We do yellow first. So you just plug them in. So you get, basically you get y, so it's negative 1 minus 3 times 1 squared over, and then 2 times the y minus the x. So you get negative 1 minus 3 over negative 2 minus 1, which is negative 4 and negative 3, so it's 4 over 3. So at 1, negative 1, we have a tangent line that has a slope of 4/3. Now, at 1, 2, let's see what that one is. Looks like it's going to be different. So let's see. So at 1, 2, we go 2. I'm using this 2 minus 3 times 1 squared over 2 times 2 minus 1, which is 2 minus 3 over 4 minus 1, which is negative 1 over 3. So it doesn't really look like it, but it looks like the tangent line there is going to be negative 1/3 of slope. So it's a slope. And there you have it. So let's try another one. All right, so this one's going to be a lot more complicated. So let's just get started with it. So we have y sine of 16x equals x cosine of 2y. And we're supposed to find the tangent line to the curve at this point. So the first thing we're going to do is we're going to take the derivative with respect to x on both sides of the equation. So d dx, both sides. So we have two functions here. We have a y, we have an f, and we have a g. We have two functions here. I'll call this capital F, and this one capital G. So on the left, we're going to do f prime g plus f g prime. And on the right, we're going to do f prime g plus f g prime, those capitals. So when we take the derivative with respect to y, we take the derivative with respect to x of y. We're doing this f prime part. We'll do 1 times and then dy dx. Anytime you see a y, you take the derivative with respect to y, and then you write down dy dx. It's the chain rule. All right, so we're going to multiply that times g, which is sine of 16x, plus f, so that would be y, times the derivative of g. So that's just 16 times the cosine of 16x. Since there's no y in this term, we don't need to write dy dx. So this is equal to, now we're at the capital F prime. Derivative with respect to x of x is just 1 times the g cosine of 2y. Plus, now f is x, and now we take the derivative of g. So that will be, using the chain rule, that'll be negative sine of 2y, and then you take the derivative of the inside. So that would be 2, and then dy dx. All right, so I'm going to clean this up a bit. All right, now what we can do is we can get dy dx by itself, and then plug in this right here. But it's easier if you just go ahead and plug these in right now. I'll show you. We get, let's see here, sine of 8 pi is 0. This is 0. So this whole thing is 0. This whole thing is 0. Cosine of 8 pi is 1. So this is 4 pi. This is just 1. All this. And now cosine of pi over 2 is 0. 4 pi equals sine of pi over 2 is 1. 4 pi equals negative pi dy dx. And so dy dx is just negative 4 when you divide both sides by pi. Divide both sides by negative pi, you get negative 4. All right, so there we have it. So we got negative 4 out of all this. So that is the slope of the tangent line at the point. And so the point is pi over 2, comma pi over 4. So pi over 2, comma pi over 4. The slope is negative 4. So we go y minus y1 pi over 4 equals m times x minus pi over 2. So that's y minus pi over 4 equals negative 4x plus, now this is going to be 2 pi. And so this is y equals negative 4x plus 2 pi plus pi over 4. And so there you have it. So this is basically y equals negative 4x plus 9 pi over 4 when you add those two together. And there you have it. This graph is not real simple to look at. Actually, you can graph it on Wolfram Alpha if you want. It looks like this. It's really hard to tell. There's better graphing functions, but if you graph it on Wolfram Alpha, you'll need to use what's called implicit plot. All right, implicit plot. And you can email me for more information on that. All right, so that's a little introduction to implicit differentiation.